Hello everyone, my name is Shohreh Iraji. Today I want to present our work entitled of Application of Unsupervised Learning for Rock Type Prediction and Petrophysical Characterization using multi-scale data. This work was done with my colleague Ramin, Soltanmohammadi, Mateus, Basso and Professor Vidal. The exploration of pre-salt carbonate reservoir is the cornerstone of South America's offshore petroleum industry. These reservoirs are very varied and heterogeneous regarding texture, pore system, and their genetic history. Reservoir rock types are rock units that accumulated under the same environmental condition, and they have the same composition, porosity, permeability relationship, pore size distribution, and reservoir quality. And also, hydraulic flow unit is a word that refers to a stratigraphic sequence that follows the same bedding planes and features that indicate rock type with similar stream speed. Rock type and flow unit determination can be used as a diagnostic tool to discriminate and also assess reservoir quality. The heterogeneous nature of a pre-salt carbonate reservoir make it really difficult to determine the distribution pattern of the petrophysical properties and also generate a clear clustering of the sample based on conventional methods. So we will have uncertainties in defining rock types and reservoir description. Precise understanding of the appropriate cluster number and also classification of rock type is necessary. Here in our study, you can see the workflow, the integration of well log and plug data. We use this both data set, and then the common unsupervised learning technique was applied to categorize different rock types based on their petrophysical characteristics and well log data. The results were then used to integrate with the conventional techniques for methods that I will present later in order to assess reservoir quality. And deep learning was employed in our study to predict porosity, permeability, and rock types in a non-cored. Here you can see the porosity permeability plot of 774 multi-well plug samples that I explained before. You can see in the figure that there is a high variability and heterogeneity, and makes it really difficult to generate clear clustering of the sample based on conventional methods. The porosity and permeability values and their corresponding well log data were discriminated into reservoir rock types according to common unsupervised classification algorithm. In the algorithm determined the center of each group and splits the data points into matching groups based on the input data. Our input data is plug samples and corresponding well log data. The number of groups can be selected using the elbow curve method. This approach works by performing the clustering problem for the input data set over a range of k-values. And the sum of squared error or SSE deviation of data points belonging to a cluster versus the cluster centroid calculated for each k. Then for these values of k, the SSE line graph is plotted. If the line chart resembles an arm, the elbow of the arm yields the best k value. So in our case, the elbow, you can see the elbow in the graph, and the elbow was chosen as an optimal value of k. In our case, it is number 4 that describes the best distribution of our samples. As I told you, using a common algorithm, the samples were classified into 4 groups. You can see in the first figure the result of porosity permeability plot based on these 4 rock types according to the clustering algorithm. In this regard, a statistical analysis was performed between different logs with plug, permeability, and porosity to find the more appropriate logs for clusterization. And the grouping was done by minimizing the sum of distance between each object and the group for cluster centroid. In the figure 2 and figure 3 displays porosity and permeability versus depth for our sample. The resulted reservoir rock types, according to common unsupervised algorithm, were integrated and supported with several techniques. The first method was R35 of Vineland. Vineland presented a mathematical model that relating porosity and permeability to the effective pore throat radius using mercury injection curves of various sandstone samples. He expressed that the foremost reliable relationship between these parameters has been set up at 35 of mercury saturation, and the link between these three parameters allow successful pore size of each reservoir rock type and hydraulic flow unit. For this purpose, the following equation that I wrote here was used, and our classified data were integrated with these techniques. The second method was flow zone indicator and reservoir quality index. Appl proposed this method to measure the quality of reservoir sequence. These two parameters were applied and tested to classify and differentiate a given reservoir into a set of reservoir rock types and hydraulic flow unit, and these parameters are calculated in the following way, and the results were integrated with these techniques. To characterize a particular set of petrophysical rock types, Cobert et al. Proposed the word petrotype, that refers to a set of global hydraulic elements, or GHE, that they define by regular sequence of flow zone indicator values and prescribed curves based on the Kozeny-Kármán equation, and have the following form. You can see the formula. In the GHE system, a regular arrangement of FZI value is selected, cluster data, and to identify separate fields with common petrophysical characteristics. When these fields follow model data that explore a particular parameter, trends can convey geological meanings, and you can see that our data in this petrotype map too. Well, here you can see the range of well-log data for all the reservoir rock types and other data in this table. For example, for reservoir rock type, it holds the best flow capacity with very good permeability. You can see that the maximum value of permeability is 726 millidarcy. Interpreting the pore space as macropores with high permeability roots. The storage capacity is less than the other reservoir rock type, with the porosity ranging from tight to fair, and the maximum is 14.9%. The highest flow zone indicator is 18.85 micrometer, and an average reservoir quality index is 2.19 micrometer. The capillary pressure and saturation curve shows the lowest displacement pressure with a maximum pore throat diameter of 25.15 micrometer, and the notation of different porosity permeability fields, or GHEs, follows 7 and 8. For reservoir rock type 2, the maximum flow zone indicator and reservoir quality index is 9.68 and 1.86 micrometer, and it is second best for reservoir quality. It has better porosity compared to reservoir rock type 1, and its range from tight to good, but the permeability is lower than reservoir rock type, ranging from poor to very good. The pore spaces are interpreted as a combination of mesopores and macropores, and the maximum pore throat radius is 20.1 micrometer, and the GHE is varied between 6 and 5. We can see the same for reservoir rock type 3 and 4. I will not mention anymore. And here, based on these reservoir rock type. Four mathematical models were created to estimate the average permeability with respect to porosity values. Reservoir quality index could be a coordination sign of the capacity of reservoir to produce and to transmit fluids. Reservoir quality index values are plotted versus permeability and porosity to examine the key contribution to the reservoir quality. And due to presence of variation of pore types in reservoir rock types, the plots indicates a relatively small contribution of porosity and permeability to the reservoir quality index values. On the other hand, for reservoir quality evaluation, the RQI FZI plot was used. You can see it in the third figure, where the two wells are defined as tight to very good reservoir with the lowest quality attributes to reservoir rock type 4 and the highest reservoir quality allocated to reservoir rock type 1 setting. Well, deep learning was employed in our research to predict porosity, permeability, and rock type. This is under process and we are improving our results. In order to identify appropriate input data required for the permeability and porosity prediction model, a statistical cross-correlation analysis of the all available well-like variables and petrophysical properties, including permeability and porosity, were conducted to determine the significance and the relevance of the features. The matrix of Pearson correlation coefficient was generated. You can see the figure. According to this matrix, the NMR porosity and permeability, neutron porosity, PIGN, deep resistivity, and quartz volume appeared as the most crucial features, and as a result, they considered as input variable in porosity machine learning approach. For permeability prediction approach, we did the same, but because it is show more heterogeneity, we are improving our result to gain a better error. You can see the error formula that we used in our study, and also you can see the error for our porosity prediction. You can see the error for training or validation sets. In our case, 90% of the data of our two wells were selected to train the network, and 10% were used for validation and testing of our model. Well, I would like to thank for Unicamp and Petro and also Equinor for financial support, and thanks for all of you for your consideration and for time.